All right, so this is 9.3, the Common Core section. We're going to do examples 1, 2, and 3. So taking a look at number 1, it says the U.S. Department of Agriculture defines heavy rain as rain that falls at a rate of 1 centimeters per hour. Now, as soon as I read that, I go to think that my equation is going to be this. Okay, it's falling at a rate of 1.5 centimeters per hour. So X represents the number of hours, Y represents the amount of rain. Okay, so that's going to be heavy, heavy rain. So number 1 says here, the table shows the amount of rain that falls in various amounts of time during a heavy rain. Complete the table. So we know that in no hours, no rain. 1 hour means that it rains 1.5 centimeters. For 2 hours, now what we're going to do is take 1.5 and multiply by every hour. So for that case, 2 times 1.5 gives 3. Then for the third one, 3 times 1.5 gives 4.5 centimeters of rain. 4 hours times 1.5 is 6 centimeters of rain. And then for 5 hours, that's 7.5 centimeters of rain. So it says here, plot the order pairs from the table of the coordinate plane to the right. So we have our time is causing how much rainfall in centimeters. Notice we do have a title here. Graph looks great. Now we're just going to plot our points. Now remember, my graph is off a little bit, but we have 0, 0. We have 1, 1.5, so right in the middle here. We have 2, 3. And the graph's going by ones here. We have 3, 4.5, so 3, 4.5, somewhere around here. 4, 6, right on the axis. And then 5, 7.5 here, so 7, somewhere around there. All right, so the question part C says here, how much rainfall falls in 3.5 hours? Now, what we can also do is draw our equation of the line here, and we can go to our graph. Now, mine's off just a little bit because I'm not plotting, I'm doing the iPad here, but you can go to 3.5 on your graph, come up, and then go over to figure out your amount. Or what we can also do is take our equation, y is equal to 1.5, and times it by the 3.5 hours. Either way, we get 5.25 centimeters. Okay, so from our graph, we can see that as well. Notice my line went down here, but that's about the point. So plotting that point on a graph would be the same thing. And it says, what do you notice about all the points that we just plotted? Well, they're all going to be a straight line. It's going to be a linear function. So 1a says, suppose that you continue to plot points for times between those tables, such as 1.2 hours and in 4.5 hours. What would we say? Well, those points are going to lie still in between. Like 1.2 would still be in between. 4.5 hours is still going to be in between. So all those points are going to still be on our line. So we would say that the points would fill in the gaps along the straight line. And then 1b says the U.S. Department of Agriculture defines excessive rain, so different from our heavy rain, that falls at a rate of 4 centimeters an hour. So in this case here, my mind's going to go to this. And it says here, how do you think a graph of excessive rainfall would compare to the graph of heavy rainfall? Well, it's still going to be linear. However, the difference between this equation versus this equation is their slope. And we know that a slope that's closer to 0 is going to be less steep, because remember that all lines that are horizontal, okay, have no steepness to them. Their slope is 0. So the further away that the slope is from 0, the steeper the line is going to be. So we say that it's still going to be linear, but it's just going to be a steeper line. All right, let's take a look at example 2. So here it says, experts recommend that adult dogs have a daily intake of 50 calories per kilogram of the dog's weight plus 100 calories. So right there, that gives our equation on the line, the information that we're going to need. So it says, write an equation that gives the recommended number of daily calories, which is y, for a dog that weighs X kilograms. So X represents our weight in kilograms. Y represents the number of calories. And as we get the title, recommended daily intake for our adult dog. All right, so here, the recommended number of calories, which is Y, is equal to, they say that the dog should have 50 calories, or 50 calories per kilogram of the dog's weight plus 100. And that's actually what we're going to put in here, okay? That's what that's going to look like here. So X represents the weight in kilograms. We're taking that and timesing it by 50. 50 kilograms per, or 50 calories per kilogram plus the 100 calories. So you can have one of those little snack packs. All right, so let's take these X values, 6, 8, 10, 12, and 14, plug them into your equation. So every X is multiplied by 50. So 6 times 50 plus 100 is going to give us 400. 8 times 50 plus 100 gives us 500. 10 times 50 plus 100 gives us 600. 12 times 50 plus 100 gives us 700. 14 times 50 plus 100 gives us 800. Okay, so those are our weight in kilograms and then how many calories the dog is going to have. All right, so let's take those points and plot them. Notice our y-axis is going by 100s. Our x-axis is going by 2s. So here we have 6, 400. We have 8, 500. We have 10, 600. We have 12, 700. And then we have 14, 800, somewhere along here. All right, so it says plot our points, then draw a line. So I'm going to draw my line. Notice that there's an arrowhead here, not here, because we can't go negative weight or negative calories. And then the equation of the linear, or the equation of the linear, the equation is a linear equation because we are a straight line. All right, so let's take a look at the check it out number 2. Graph the solutions of the linear equation, then explain how the graph is different from the graph in example 1. All right, now remember, there's multiple ways that we can graph this. You can graph this with plotting 3 points, negative, positive, and 0. You can graph using the both x and y intercepts, or remember we can graph from slope-intercept form. And I think slope-intercept form is the easiest. So in this case here, our y-intercept is 1. When x is 0, y is 1. And then our slope, change in y over change in x, is negative 2 over 1. So I'm going to start the y-intercept, which is 1. Then I'm going to go down 2, over to the right 1, or I can also go up 2, but then to the left 1. So up 2 and to the left 1. And our graph's going to look something like this. Now, how is it different from the example that we just did with the dog? Well, one thing is that your slope is negative. Okay, so notice that when we're reading this graph from left to right, the line goes down. And then the other thing is that graph 1 is just in quadrant 1, but here we're in all 4 quadrants that you've got arrowheads on both sides. All right, let's take a look at example 3. So example 3 says here, the square tile has a side length of x inches. And because it is a square, that means all your sides are the same. So x, x, x here, okay, is all of our dimensions. The equation, y is equal to x squared, gives the area of the tile. Because remember, for area, it's side times side, or we can write that as side squared. Okay, so since our side represents x, we say x squared. Determine whether the equation, y is equal to x squared, is linear. Now, we've done this in class before. We know that in order to be linear, it has to be in slope-intercept form, where x is raised to the first power. Here, automatically, because x is raised to the second, it is not linear. All right, so these are my side lengths. It could either be one, measure of 1, measure of 2, measure of 3, measure of 4, and we're in inches. So 1 inch, 2 inch, 3 inch, 4 inch. So if my side length is 1, my area is 1 times 1, or 1. 1 squared square inch. If my side length is 2 inches, 2 times 2 gives me 4 square inches. If my side length is 3, 3 times 3 is 9 square inches. And if my square has a measurement of 4 inches on each side, then that would be 16 square inches for my area. So now graphing them, make sure that we label. On your x-axis would be inches, on the y-axis would be area, and then here you can write anything for your title. We have our square tile if we wanted to. All right, so in this case here, we're going to plot our points. So we have 1, and notice that the graph's going by, on the y-axis, it's going by 2s, 2, 4, 6, 8, but on my x-axis, we're going by halves. So 1 and then 1 would be like a little below that. And then we have 2, 4, 3, 9. So 9 would be somewhere around here. And then 4, 16. And notice, oh no, I just moved that all. Sorry, I just moved that, but that's what your graph would look like in this case here. Now remember that if we would continue this and pick some negative values, remember that would make our U-shaped as well. All right, so it says here, decide whether the equation is linear, and that's going to be no, because it is a U-shaped graph, because x is raised to the second power. It's not going to be a straight line. These graphs grow exponentially because x is raised to the second power. So 3a says here, how is the equation y is equal to x squared different from the linear equations that we graphed? Well, here, because the variable is raised to the second power. Okay. 3b says, explain whether you think the equation is linear. Y is equal to 2x to the second plus 4. And we're going to say nope, because x is squared. And then 3c says here, a student graphed several different solutions to this equation here, y is equal to negative 2x. The student concluded that the equation is not linear. But what's wrong with this? Well, if I'm looking at it, it almost looks like a U shape or a V shape, like an upside down one. And we know that if we had an equation like this, that would be an upside down U anytime they got the negative in front, because it's going to flip every negative. But what happened here is that when they plugged in negative 1 and when they plugged in negative 2, they still kept their values as negative. They should be up here when you plug in those negatives, because if it's just raised to the first, that front negative here, negative 2 times negative 1, creates positive 2. Negative 2 times negative 2 creates positive 4. So those are the y values should be up in the second quadrant, not the third quadrant. All right, so today you're going to continue and do the next page here, which is the practice 1, 2, 7.